G'day guys, this is going to be a video on Walding chapter 21. We're going to look at the in-text questions. We'll try to go through questions 1 through to 6, definitely 7, 8, and 9, and looking at 10 and 11. Let's see what else is in that section. 10 and 11 we don't need to really worry about potential difference, but we'll take a look if the video doesn't run too long. Let's get started. So question 1 is reading here, use the triboelectric series to describe the outcome of rubbing, and we've got a few different options here. So let's have a look. So our first ones are glass and silk. Now remember, triboelectric series is about how likely something is to give away an electron or attract an electron when in contact with something else. So if we scroll back up to our triboelectric series, and it's on page 446 in your textbook, we're looking for our two things, glass and silk. We see that glass is about halfway through the positive and silk is quite close to neutral here. Now the fact that silk is neutral doesn't mean that silk is going to be neutral. It just means it's not really a giver, not really a taker, it's kind of in the middle. Glass, however, is very much up towards the positive end. So this means being as glass is above silk, glass is going to end up being positive and silk is going to end up being negative. Let's have a look at our next two. Now our next two are rubber and wool. Rubber and wool. Again, if we take a look at the list, we see that rubber is quite low down at the bottom, about halfway to 2/3 through the negative section, but wool is quite clearly up in the positive area. So wool is going to donate electrons, it's going to give them away, and so the wool is going to become positive, which means the rubber has to be negative. Finally, C, our two are gold and cat fur. Gold and cat fur. And taking a look at our list, we see that gold is way down on the negative side. It's the highest there for affinity for electrons, while cat fur is all the way back at the top. So gold will end up being our negative, meaning cat fur will end up being our positive. Okay, question 2. Let me just scroll back to question 2. Question 2, here we go. Draw a diagram showing the electrostatic outcome of two perspex rods rubbed with silk cloth and freely suspended in close proximity to each other. Okay, so we've got, this is again triboelectric stuff, the fact that I'm mentioning that the perspex rods are being rubbed with silk cloth. So we've got perspex and silk. Let's see what happens. Now, the one thing that we can say is that because we have perspex and silk together, the outcome is going to be the same. The two rods are going to end up being the same charge, which means they're definitely going to push away from each other. So I'm just going to draw that to begin with. Let's say that I've got one rod. That was got one rod and we've got another rod. They are both perspex. The force on them is going to be pushing away because they're both going to have the same charge. What charge? We don't know. Let's go back up to our thing. Now there are some pictures of rods sort of hanging near each other on page 447. I mean, I'm not looking for something with any sort of level of artistic talent like that. If we go to our triboelectric series though, we've got perspex and silk. Perspex is very high on the positive side, so it's going to donate electrons. Silk, as we saw before, was around the middle. Excuse me. However, that does mean that silk is going to receive those electrons from the perspex, meaning that our perspex rods will end up being positively charged. Now, as I said before, it doesn't matter what they were going to end up being. They could have been negative charges. They still would have been repelled. Remember, opposite charges attract, same charges repel. Being as we did the same thing to the rods, and the rods were made of the same type, they were both rubbed with silk, then we knew that they were going to end up being repelling. What actual charge really didn't matter too much. However, for a completeness of this sort of thing, applying the triboelectric series to identify what was positive, what was negative, would be good. Let's have a look at 3. Okay. Draw a set of diagrams to explain the outcome of bringing the following within close proximity of, but not touching, a neutral electroscope. Okay, so with a word like electroscope, you should be looking up to see, well, what is an electroscope? And I believe there is an example of one just a bit up higher. They talk about electroscopes on page 450. So whenever you're looking at things saying, oh, well, I don't know what this actually is, do check your textbook, because the textbook is not going to say, oh, talk about this apparatus without generally providing some information about it. The electroscope, we had one in class, was the small conical flask with the gold foil inside of it, and I showed bringing the charge rod near it, and we saw that the foil would curl up. However, if I touched it, then the foil would stay standing up. Now, the fact that they've mentioned two different charge rods there don't actually matter. They're going to be exactly the same result. Whether it's negatively charged or positively charged isn't a particularly big problem. So physically it's going to look the same. But what will happen is just where the charges are actually going to be. So let's draw the first one. For my electroscope, I'm going to draw just a single line with another bit coming off it. That's my foil. Let's put a circle around it to show that it's isolated. Put a plate on the top, and I'm going to bring a positive rod near it. Now, if this thing is positively charged, oh sorry, the first one was negative charge, let's do it negative charge. Negatively charged. So if I bring a negatively charged rod here, it's close but it's not touching, which means that all the electrons at the top here are going to end up rushing down to this side, okay? Leaving this area at the top more positive. Remember that electrons can move around freely within a substance, and so if I bring a charge near it, then we're going to end up pushing away those electrons. And so then, being as now this section here is negative, we're going to end up looking like this. It's going to move away from each other. Remember, we saw this in class. That area down there will be negative, this area at the top will be positive, and we'll still have our rod that is negative. Now, if it's a positive charge rod instead, we're going to bring our positive charge rod near it. Then electrons from here are going to rush up the top because, you know, there's this extra positive charge and the electrons want to be near it. They're little hussies, leaving this area down here to be positively charged. And because it's positively charged, it's going to end up splitting, while the top will be negative with our positive rod. Now, if we take away either of these rods, then it's going to go back to how it was before. So it'll just revert to a neutral state. The charge will go, oh, there's too many negatives up here. Oh, there's some positives down here, and some will rush down, and there we go. All right. So when we're dealing with electrostatics, if we don't touch, as soon as we move away, it's going to revert back. If we did touch, then the charge difference will maintain, unless it's this one won't, because the electrons have flown away from it. However, there'd probably be a little bit of charge distribution because some of the electrons here will flow off onto that. This one will quite definitely stay apart because the electrons will happily jump ship, and leaving this electrode behind to be positively charged left over. Remember, when something is neutral to start off with, we assume that everything is identical. There's exactly the same number of protons as electrons, and so charge is cancelled. Let's have a look at 4. In a particular chemical reaction, an iron atom, Fe, becomes a ferric ion, Fe3+. So let's write that down. Fe becomes Fe3+. This is interesting, 3+. That means that it had to lose 3 electrons. So let's write that, therefore, lost 3 electrons. Let's keep reading. Determine the charge on this ion in coulombs. Describe what has occurred in terms of electron transfer. Oh, okay. So we've answered the second part there. It's lost 3 electrons. If it's become positively charged, it had to lose an electron. What is the charge of this ion in coulombs? Well, we've lost 3 electrons. Oops, I missed my E for my electrons. So if we've got our electrons here, then we need to know, well, how much charge is there on 1 electron. Now, if I scroll back up through my notes to find that number, okay, so remember that an electron has charge of 1.602 times 10 to the negative 19 coulombs. Remember, that was a number we talked about in class. This is one of those constants. This is not something you would have to remember. You should definitely have it somewhere in your notebook as you're doing work and questions, so that you're used to looking in one single place to find important numbers like that. However, if I expected you to use it on an exam, it is something I would give you on an exam. We want to know for this question though, well, what was the charge? Determine the charge on this ion. Now, the fact that it's lost 3 electrons doesn't matter. It's still going to be 3 times this charge, so 3 times 1.602 times 10 to the negative 19 coulombs. Remember, coulombs can be positive or negative. And 3 times 1.6 is going to be about 4.8. So 4.8 times 10 to the negative 19 coulombs. The fact that it's a positive charge doesn't matter, so I'm just going to write positive out there. If it had gained 3 electrons, it would have been negative 4.8 times 10 to the negative 19. It's still going to be the same amount of charge. All that's sort of different because it's lost electrons compared to gaining electrons is how whether it's positive or negative, okay? Just remember, we're talking about charge on things, we're just talking about electrons moving about. Let's have a look at 5. Consider figure 21, so that's off to the side there. A and B are identical insulated metal spheres with charges shown. So that means that they're kind of sitting there, but the charge can't move around. What is the charge on each sphere after they are touched together and then separated? Okay, so let's think about this. Let's draw our 2 spheres. We have an A and we have a B. Okay, so we're just looking at A, so that's plus 8, and that's minus 4. They're both microcoulombs, so these are identical. Okay, now, these are identical metal spheres. Okay, so that means they've got the same mass, they've got the same volume, they've got the same area, everything about them is the same. All that's different is the charges. So instead of writing this as plus 8 and minus 4, I'm going to write this as the number of pluses. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Now if we were to touch these together, 1, 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, then the electrons will be free to move evenly. Now, some of them are going to go over to this side, and some of them will move backwards. However, what's going to happen is the charge is essentially going to neutralize. Right now, this has 4 extra electrons. So if we got rid of all these 4 extra electrons, this would become 0. And this would then be plus 4. We can see then the charge is still unbalanced. Okay, so I'm going to draw that second stage. So that one's going to be neutral. Let's put an N for neutral. And this would be 1, 2, 3, 4. It's still going to need to pinch a couple of electrons, basically, is what I'm trying to say here. So all these electrons have jumped ship. We end up with, that's neutral. We got rid of its extra 4, but that's still unbalanced. And we can say, all right, well, let's steal another 2 electrons to cancel off 2 more. And we will find that we have 1, 2, 1, 2. Now they're identical, they've got the same charge, yeah, they're both positive, that doesn't matter. What we're talking about here is that everything has spread out. But we've got to treat this as a thing, so remember we had plus 8 and minus 4. I mean, if we add these 2 together, then we're going to end up, so plus 8 minus 4 equals plus 4. Right? And we have to have plus 4 over 2, because, you know, there's 2 different poles. And so we can see, oh yeah, each ends up being plus 2 at the end of the day. Okay, remember this is plus 2 microcoulombs each. So that should be a capital C. Let's head into 6. Figure blah blah blah, 21.10b, A and B insulated spheres. This time sphere A has twice the radius of sphere B. Well, the charge in each sphere as they touch together and separated. Remember, charge resides equally distributed over the surface of a spherical metallic conductor. So when we talk about this charge here, it doesn't lie inside of it. So if we were to take a sphere or a big circle, let's take a big circle like we're cutting into the middle of a of a big sphere, like a big bowling ball, what we would find is that all the charge hangs out on the surface. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is sphere A. None of it sits inside of it. Okay, and that's important to remember. This always happens. The reason being is that if I had a charge, say here, these ones here being very close would be pushing it very hard. These ones wouldn't push it as much, so it'd head towards the middle. But because it's got a force sort of pushing it towards the middle, it's going to end up getting pushed past it a bit more. We can't end up with this charge being evenly spread. These ones on the outside can't go anywhere, but this one here can keep moving, and so unless it was sitting right in the center, perfectly balanced, which it never would, it is going to end up getting pushed out, and so it does end up on the surface. Okay, so the charge is always at the surface of an object. If we have a look at sphere B, it is -5. 1, 2, 3, 4, 5. Now, the spheres are different size. Let's have a look at the difference in size. A, B, charges shown, so twice the radius. So, radius A equals 2 times radius B. We want to know the surface area, so we're going to need to know the surface area of a sphere. Now, I can't remember that formula off the top of my head, so I'll do a quick Google search. Surface area for a sphere, formula is 4 pi r squared. Right. That sort of geometry I'm probably not going to worry too much about in terms of an exam. Really simple geometries like areas of circles and triangles, etc. That sort of stuff I'd expect you to know. But areas of spheres, yeah, we don't work with them too much. But let's have a look at the comparison of the area. We know that the radius is twice, but what is the size of the surface area? So surface area equals 4 pi r squared. So area of A equals 4 pi 2rb all squared. Remember, the whole thing needs to be squared because the radius is squared, not just the radius of B is squared, equals 4 pi times 4 rb squared equals 16 pi rb, while the area of B just equals 4 pi rb. Now, let's see how much bigger is that compared to that. 16 pi rb over 4 pi rb, cancel, 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 16 over 4 equals 4. So, this area is 4 times the size of this area. This sphere can take 4 times as many charges as this sphere. So the first thing I'm going to do is this. I'm going to do the same thing where I'm just going to sum up what the charge is going to be. I have plus 10, I have minus 5. Before we even care about imbalance of charge and the spreading of charge, I need to just cancel things off, and we can see that means I'm going to end up with plus 5 left over. Interestingly enough, 5 is a nice number for a multiple of 4 to go into. Sorry, not multiple, that's what I'm looking for. A ratio of 1 to 4 to go into, because a ratio of 1 to 4 means 5 equal parts. Okay, so 1 part on one, 4 parts on the other. So we're dealing with 4 times, and you know, if there's 4 parts in one part of the ratio, 1 part on the other part of the ratio, that's 5. Alright, so let's draw our spheres after the first bit. So they've touched together. All our negatives have gone, so I've got 1, 2, 3, 4, 5. This baby's neutral. If we move 1 charge over to here, 1, 2, 3, 4, and on B we have 1 charge. We can see we have a 4 to 1 ratio, we had a 4 to 1 surface area, we have all the charges that have been not cancelled still chilling out, because you know, like one of these ones is going to bump over there. I know we're talking about the movement of electrons generally, but you can sort of think about the movement of positive charges as well. It's still equally as valid. Well, what's really happening is that the electrons are the things moving. However, what we see is the result of this positive charge. So there's our first 6 questions. I hope that sort of made that sense. Now the next ones do require force calculations, and I'm thinking about doing another video on doing vectors, which is a sort of reminder for people. However, Khan Academy has some excellent videos on solving vector sums, both in the drawing method, using the sine and cos rule for triangles. Note, I don't mean sine and cos for trigonometry. There are some more advanced ones that you should have seen in your math class. If not, we'll make a video anyway regardless. However, not tonight. Let's go on to question 7. Within an atomic helium nucleus, 2 protons are separated by a distance of 1 times 10 to the negative 14 meters. What is the size of the Coulomb repulsion force between them? So atomic helium nucleus. So helium removes 2 protons, 2 electrons, and it's also 2 neutrons. And we have a distance between the 2. Remember, so let's think about this. We have our protons. So a proton has the same charge as electron, equals, it's just positive, 1.602 times 10 to the negative 19. So we have Q1 equals 1.602 times 10 to the negative 19. Look, I'm going to do, sorry, I know I gave the formula with lowercase q, I'm just sort of used to writing uppercase q. Q equals 1.602 times 10 to the negative 19 as well. They are both positives. We know that the distance between them, we use r for sort of radius, but d for distance is equally fine. And they've said here that it is 1 times 10 to the negative 14 meters. 1 times 10 to the negative 14 meters. And the question is asking, what is the strength of the repulsion force? So we are after a force. Remember, we covered Coulomb's force equation in class this week. So force is going to equal, or force electron is going to equal Coulomb's constant, Q1, Q2 over R squared, equals 8.99 times 10 to the 9 times 1.602 times 10 to the negative 19. We're going to multiply that twice because they're both the same, so I'm just going to do a squared. I hope that makes sense. 1 times 10 to the negative 14 squared. Now, you'll notice I've put my powers here in brackets. This is a very important habit to get into, because if your calculator skills are a little bit sloppy, then you will not square the right thing and you will end up getting the wrong answer. So do be aware of that. Remember, calculators are exceptionally stupid. It is always best to do these things with a little bit of extra bracketing. Okay, I've managed to lost my calculator, so I'm just going to type this in a Wolfram Alpha. So 1.602 times 10 to the power of negative 19. And all of that is squared. And we're going to divide that by 1 times 10 to the power of negative 14. We are squaring that. And then I want to take the whole thing and multiply it by 8.99 times 10 to the power of 9. And yep, let's put that in correctly. And we get that is equal to 2.3 newtons of force. Let me double check our answers there. Question 7. 2.3 newtons repulsive. Okay. Alrighty. Let's have a look at question 8. 2 point charges A and B each have a charge of plus q coulombs and are separated by a distance of r meters. If the force acting between them is 6 times 10 to the negative 14, is the force attractive or repulsive? What is the force if distance r is doubled? What if the force if charge on q both A and B is doubled? What is the force if charge on charge q on both is half, but so is the distance between them? Okay, let's go through this. So what we're dealing here is looking at how one side of the equation would change if we change the other side of the equation by a proportion. So let's start off. Force acting between them is 6 times, each have a charge of plus q coulomb. So we don't even need to worry about anything for this. It's plus q. Q could be 1, Q could be a billion, Q could be 0.0002. It doesn't matter. They've said plus coulombs. They're both plus, therefore it is repulsive. Both plus, therefore repulsive. Okay, nice and straightforward. Remember, when you're answering these sort of questions on exams, you don't need to write big long sentences. These four, if this was this would be a C standard type question. These 4 words would get you a C. You could write 2 sentences long saying stuff like, because both the charges are positively charged, even though we don't know the size, therefore the force between them will be repulsive as same signed charges repel. That would also get you a C. Okay, 4 words get you a C, 20 words get you a C. There's no, with the C standard type question, remember they're always marked. Going excessively long into depth doesn't get you bonuses, but okay, be smart about how you answer questions. Let's have a look at B. We know that the force, just write this off to the side, is equal to 6 times 10 to the negative 4. Let's have a look. What is the force if distance r is doubled? Okay, so the equation F equals, well actually we're not even going to worry about the equals because it's proportional. F is proportional to Kc, well don't need the Kc because that's not going to change, Q1 Q2 over R squared. So this is our first bit. Let's imagine that R is equal to 1. Okay, then force is just going to equal to the product of our 2 Q's. But if we made R 2, then our R squared would go to 4. So if we double our thing, then we're going to end up quartering our force. Does it? I hope that makes sense. So what we're saying here is that if I go, well, if R1 equals 1, therefore R2 equals 2, therefore R2 squared equals 4. So F would be proportional to Q1, Q2 over 4. So see how now we're dividing by 4 instead of dividing by 1. So R1 squared would equal 1. Now okay, but what if R1 was equal to 3? Okay, what if there was 3 meters between the two? Well, it doesn't matter. Okay, so if R1 equaled 3, then R1 squared would equal 9. Remember, we're doubling the radius. Okay, we're doubling the radius. Not saying increase it by 1, we're saying we're doubling the radius. So R2 would equal 6. So R2 squared would equal 36. And 36 over 9, the ratio is a 4th again. Okay, these sort of questions are not inherently anything to do with physics. It's just about ratios, proportions, and how do formulas, it's basic algebra and how formulas work. So we knew it was 6 times 10 to the negative 4 divided by 4 is going to equal 1.5 times 10 to the negative 4. Which, if you have a look in your answers there, you'll see that that is correct. Okay, let's have a look at C. What if the force on charge Q, both A and B, is doubled? Okay, so again, let's say Q1 and Q2 were both 1. Let's make them Q1 and Q2 both 2. Okay, because 2 is double 1. So then instead of 1 times 1 for our Q's, okay, we'd end up 2 times 2, which is times 4. So it's going to increase by 4 this time. Okay, and okay, let's do the math on that. So let Q1 and Q2 equal 1. Therefore, Q1, Q2 equals 1 times 1 equals 1. If Q1 and Q2 equal 2, therefore Q1 times Q2 equals 2 times 2 equals 4. So F, in this case, would be proportional to 4 over r squared. The radius hasn't changed, so it doesn't matter. We've just increased it by 4. Now, this sort of working out here, you don't really need to show. This is so that I can demonstrate to you why it is what it is. You don't need to do this on an exam. You would just need to tell me, oh, yeah, we've doubled the top, so therefore it must be 4 times as large. Okay, the sort of understanding of how formulas work, you don't need to explain those terribly to me. Now, if the question said explain and justify why it's 4 times larger, then you would, because that's a coordinative verb where you need to go really deep. But if it just said, you know, the question here is, well, what is the force? It's not a great language that I'd use. I'd more use calculate what the force is, in which case it's a straightforward sort of do the math without proving it. You just have to show it. But again, don't overly worry about this. So it's going to equal, what was our number? 6 times 10 to the negative 4 times 4 this time. So instead of dividing by 4, we're multiplying by 4. We're going to end up with 24 times 10 to the 4, negative 4, sorry, equals 2.4 times 10 to the negative 3 newtons. Remember, always convert back to scientific notation. Okay, let's have a look at D. Both charges are halved, but the distance is halved as well. So again, let's do the same thing. So if Q1 and Q2 are both 1, if we halve them, they're both 0.5. So 0.5 times 0.5 equals 0.25, or 1/4. So if that's Q1 and 2. However, the radius is now 0.5 squared equals 0.25. So we're going to have 0.25 over 0.25. So therefore it would cancel, because the top's going to be reduced, well, the proportion is going to be reduced by 1/4, but the bottom's also going to be reduced by 1/4, and so we're going to end up with, you know, the quarters cancelling, which equals therefore same force. Sorry, same is spelled with a M, not an N. Okay. Again, that question is not really about electrostatics. It's about manipulating equations so that you can see the relationships that are going on there. I would encourage you to maybe do some experimentation with numbers. Start off with Q1 and Q2 both equaling 1. Say double Q1 a few times to see what happens, double Q2 a few times, see what happens, double both of them together a few times, so yeah, 1, 2, 4, 8, etc., to see what happens. Do the same thing with radius to have a look at the numbers and look at how the numbers relate to the forces. If I double radius, what happens to the force? Now we've seen it should go down by 1/4, but give it a test. Okay, there's nothing wrong with that. Question 9. 4-point charges A, B, C, D are arranged on corners of a square. The sides 25 centimeters. A and B both have a charge of +1. C and D each have a charge of +2. What is the resultant force on a charge of +1 placed at the center of the square? Cool. Okay, big one. So we have 4 charges. Now it doesn't matter which way you label it. I'm going to label it sort of top to bottom and call this one P. Now we said that A and B both have +1 microcoulomb, +1 microcoulomb, +2 microcoulomb, +2 microcoulomb. Now, if we look at this logically, we can see that A and B are going to, this one here is +1 as well, +1 microcoulomb. This charge is going to push it that way, this charge is going to push it that way, this charge is going to push it that way, this charge is going to push it that way. So if we look at these in terms of pairs, say A and B are both going to push it up, and C and D are both going to push it down. They're things that we need to care about. A is going to push it that way, B is going to push it that way, C is going to push it that way, D is going to push it that way. Now, what's useful about this is that A is pushed that way, so A is going to push that way and B is going to push that way. They're going to cancel each other, they're not actually going to move it. C and D are going to do the same thing. C is going to push that way, D is going to push that way. These two have the same strength. Their sideways pushes are going to cancel. So all we're going to deal with is some up and down. Now C and D are both going to push down. A and B are both going to push up. A and B are both half as strong as C and D. So they are going to end up 25 centimeters pushing down 0.25 meters. So we need to know then, well, how far away these charges, so we can work out how strong the push is. We also need to then know what angle these things pushing at, so that, or not even, what angle are they at, so that we can work out what it is, because the downward push from D, the push from D is going this way, so D's pushes that way. We need to know, well, how much is going to go straight down, because the same thing will come from C, so at least we don't have to do the math twice, and it is a square, so all distances should be equal. We'll also have to need to know the push from A and B, because they're going to push up, and then we'll have to cancel it. So let's work out, let's just draw C, D and P for the moment. C, D and P. I know that that is 0.25 meters, and because this is a square, then the distance from each corner to the middle will be identical. Because it is identical, then I know that these angles in here will also be identical. So given that, because this is, if I split that down the middle, then this will end up being, because it's an isosceles triangle, if I perpendicularly bisect an isosceles triangle, then I will end up with two equal size pieces either side, each at 0.125 meters. From this, I'm going to need to work out the angles inside. Which should be 45 degrees. Don't even need to worry about what's the word I'm looking for. Any sort of isosceles triangle rule. So C, D, P. The reason being is this is a square. Okay, these squares are all going to be identical. These triangles around it are always going to be identical, which means that all these angles will all be identical. And being as, that's going to have to be 90 degrees because it's the corner of a square, that means this and this are going to have to be identical, which means that they're both going to be 45 degrees. And that's going to be 0.25 meters, 0.25, and that would also be 45 degrees. Let's see, well, actually, a couple of ways I could do this. I could use this I could use the sine rule to work out one of these two sides, and they're going to be identical. So once I've got one, I've got the other. I could use, that's going to be a right angle. So I could use Pythagoras Theorem, nice and easy. Because it's a right angle triangle, these two are the same. I'm going to have a squared plus a squared equals 0.25 squared. So a squared equals 0.25 squared over 2. Let's calculate that. Oops. Uh, 0.25 squared over 2 equals, and I need the square root of that. 0.176. No, 177. Let's round up. Move this step here just in case I need it. 0.03125. Having an exact value might be useful sometimes. Okay, so I now know that each of those sides is going to be 0.177. So looking at this, I have point P and I have point D, and I know that the distance between them is equal to 0.177 meters. I know that this is +1, I know that this is +2, and they're both in microcoulombs. Now we can work out the force between them. I know all this stuff up here was tricky, this geometry part, and so I'm saying that this earlier math stuff that you've done through grades 7, 8, 9 and 10 is going to be so important, because these sort of questions get thrown at you a lot where you need to think about just some basic geometry. The thing is, the more you do them, the easier they get. I've done problems like this a dozen times. Once you've seen a trick once, it's generally pretty easy to spot the trick again. There are very few different ways they can set up a tricky type of question, and commonly the trick is actually in this geometry part. It's not the physics so much, it's in this stupid geometry. So once you've got the hang of recognizing that, then you're going to be off to a good start. So let's work out the force between P and D. So force between P and D is going to equal Kc Q1 Q2 over R squared, 8.99 times 10 to the 9 times 1 times 10 to the -6 times 2 times 10 to the -6. Remember, Coulomb micro is 10 to the -6, 0.177 squared. Okay, what's kind of cool is that the force between P and say B, because force B and A will have the same, will have almost identical things, but instead of having a 2, we'll have a 1 there, so we've got 1 times 10 to the -6 times 1 times 10. Forgot my Kc. Be careful about those Ks. 8.99 times 10 to the 9 times 1 times 10 to the -6 times 1 times 10 to the -6 divided by 0.177 squared. Now, the secret thing is I wouldn't actually do this a second time. I'd just take this and whatever answer I get out of here, and I'm just going to divide it by 2, and that'll give me the answer to that one. So I'm going to plug this first one into Wolfram Alpha to solve for me. So 1 times 10 to the -6 times 2 times 10 to the power of -6 times 8.99 times 10 to the power of 9. Good. Yep. Divided by 0.177 to the power of 2. Squared that. Okay, if you're using a web program to do calculations, always just double check that you've actually put it in right by looking at the input interpretation part of it. And it is this very long repeating decimal, but that's okay, we only want the first little bit. 0.574 newtons. And now I will go and change the 2 to a 1. And that's going to give me what's that going to be, 28-ish, 287, 0.287 newtons. Okay, so we've got our 2 forces. But what we've worked out here is, well, how much force is being pushed that way, and how much force is being pushed that way. We've got how much force is going that way, and how much force is going that way. So we could use those numbers to then reduce it and work out, well, how much is actually acting this way and this way. The other alternative is we work out how much force is actually acting downwards and horizontally for each of these things, and work out from there. Now, I kind of prefer the second method because we originally drew it like this. A, B, C, D. Okay, what we have at the moment on point P is we have this force, this force, this force is going to be bigger, and this force is going to be bigger. Let's work out, let's do it both ways. So let's firstly sum up along this line. So the force of A on P is going to equal the force of B on P, which we worked out as being 0.287, and let's take that force in that direction as being positive. It doesn't matter what. The sign really doesn't matter in this case. Remember, the sign is about direction, not whether something's attractive or repulsive. It's just about direction here. And the force of D on P is going to equal 0 or negative 0.574, because it's actually in the opposite way. And if we add these together, we find out that the sum of forces on that AD line equals negative 0.287, and the sum of forces on the CB line will equal the same, negative 0.287. So if we draw our P point, we have 0.287 acting that way, 0.287 acting that way, and we can see that, well, that's the same either side, so it's going to be some force down there. We'll call that force total. Now, if you throw your mind back to the last time we did vectors, so grade 11s, it would have been hopefully in 10 extension, and for year 12s, it would have been the previous year. What we're doing here is we're adding vectors. When we add vectors, we can draw them top to tail. Okay, so because these are right angles, and these are at right angles to each other, the angle between these is 90 degrees. Remember, that's because this internal angle is 90 degrees, as we saw when we were doing some geometry back up here. So that angle is still 90 degrees. They're perpendicular to each other. We don't have to worry about breaking them, decomposing them at all. So we're going to end up with a right angle triangle. We're going to have this 0.287 plus this 0.287, that's going to be 90 degrees, so that's going to be 45 degrees, and that 45 degrees will mean it's going to go straight down, which is what I've been telling you from the start. And we can see there, well, we don't know what that equals. So hypotenuse squared equals 0.287 squared plus 0.287 squared. Let's chuck that in. So 2 times that, square root, and that equals about 0.406 newtons down. And if we go to our answers, which question? Wrong question, 9. Well, that's interesting. Interesting. Okay, so I read this as saying A and B are going to be down the bottom and C and D are going to be up the top, and that's how I drew the picture. Now, the answers in the textbook says, it's 4.1, which is what we got. I've gone to 3 decimal places. They've said up the page. How could it go up the page when we've got down the page? Who's right? Who's wrong? Well, there's no statement here about what order that is in. What if instead I drew it as A, B, C, D? What if I drew it as A, B, C, D? All that matters is the size. Okay, there's no actual thing. Now, like on a question like this, if I gave you question 9, I would probably give you a picture of the question to say, oh yeah, here's my square, here's the order I want you to do the points in. But if you drew this picture here, you go, oh yeah, A, B, C, and D, I can't mark you down for it. And anyone who said that, who tried to do that is bloody pedantic and stupid, so I'm not going to do that. So just be aware of stuff like that. Like if you've done all this math and you go, oh crap, I've got to go down the page, and I've got to go up the page, and you put the same number, then you've got to think about what were my original assumptions right back at the start. Now, the thing about this, so there's two major things in here. One was the geometry at the start. Now the force between them, that's just Coulomb's law. That's nothing we haven't seen before, and I really don't think that should be much of a trouble for you to wrap your head around. Remember, two particles, any charged particles, there's going to be a force between them. It might push, it might pull, that's okay. This geometry of vectors, that's stuff from previous years, and you're going to have to, get on top of those as you're doing it. Unfortunately, we don't start with motion first, so you do have to do your best for that. You need to do extra study. If it's puzzling you, you've got to do extra study. It's not going to get easier unless you do that extra study. Now, there was another way to do this, this last bit here, in that if we took this 0.287 down to the southwest and worked out how much was going south first, we would find that we'd end up with, I'll draw it out. So let's say that we had 0.287, because that's 45 degrees, because it's half of 90. We can then work out, well, how much is going that way, how much is going that way. The good thing is that's a 45-degree triangle. These two sides will end up being the same. It'll be isosceles. So that'll be A and that'll be A. So we'll have 2A squared equals 0.287 squared. That is just me using Pythagoras Theorem very quickly. I would recommend that you get familiar with that. So let's use that number from 0.287 squared, and y through, and then take the square root, and that's going to equal 0.203. Now, that's how much is going down, it's all how much is going across. For this other one, it's going to be the same thing. 0.203 down, 0.287 is the hypotenuse. We're going to have 0.203 across. Now, this across and this across, left and right, they're going to cancel. So we're just left with this down plus this down. So 2 times 0.203 equals 0.406 equals what we got over there. So that should be a 6. As I said, it didn't matter what way we did it, and honestly the math is pretty much the same regardless of how you do it, but vectors is just one of those things you've got to get used to. I'm happy to give extra help, and remember, year 11s, you've got that time to practice in Tuesday morning classes. However, you're going to have to do it sometime or another, so get into it now. Last 2 questions for homework are questions 10 and 11. Let me scroll down to those. Let's have a look at this. So question 10. Draw the cross-sectional electric field diagram for a system of negative charges, all situated at the corners of an equilateral triangle. Okay, equilateral triangle, so let's draw that. Equilateral triangle, this distance, and this distance, and this distance will all be the same, because it's equilateral. They're all negatives. Remember that field charges flow into negatives and away from positives. So the thing is, like, this is going to have a repulsive force on each other. They're kind of gonna flow into it, but it's not going to go into this middle. You can think of it like, oh yeah, this is pulling and this is pulling, and anything here in the middle would feel an equal pull between. There'd be a bit of a further pull over there, but let's ignore that for the moment. So you're going to have some pretty diagram like, oh yeah, it goes in there and in there and in there and in there, and then over this side will be something similar like, oh yeah, in there and in there and in there and in there, and then around here we might have just there'd be stuff on this side as well. It's just something to that extent. So if I look at this, we've just got that it's an equilateral triangle, they're all negative. There's going to be nothing in here though, because unless there was a positive charge in here, like if it was a positive charge, then yeah, there'd be stuff flowing to there. Okay, but because there isn't a positive charge in there, then nothing flows that way. Okay, any positive charge out here is going to flow to one of the, like even like one here, and it's all going to flow either way. It's not going to get into the middle, so that bit in the middle has to be empty. Okay, let's just write that must be empty. Okay, because all the positive charges is outside. It hasn't said that there's any positive charge on the inside. And question 11. What is the electric field strength 0.2 meters from a point charge of minus 0.6 microcoulombs in both magnitude and direction? Okay, so let's look at our field equation. So we have two field equations. Electric field is either equal to force over charge, or electric field is equal to kc q over r squared. We have a charge, q equals negative 6 times 10 to the negative 6, and our distance is equal to 0.2 meters. So we can see we're going to be using this equation here. So E equals 8.99 times 10 to the 9 times 6 times 10 to the negative 6. Whoops. Divided by 0.2 squared. And let me just load up my calculator to do that. And we're going to get a magnitude. Now I haven't bothered putting the negative in, I've just put the magnitude of, this is a pretty big number, 1.35 times 10 to the 6 newtons per coulomb. Okay, so we've got our magnitude, and if we do quickly double check our answers, we see 1.35 times 10 to the 6 newton per coulombs. Good. Now, we said that the charge was negative. Let's go back to the question. Yeah, negative 6 microcoulombs. Remember that when we're drawing electric fields, we're considering what would happen to a positive test charge. Okay, it's a positive test charge. So if I put a positive charge near a negative 6 charge, what's going to happen? Opposite charges attract. The positive charge is going to get pulled inwards. So we would say that it is inwards in size. It's kind of cool, it's like that negative tells us that it ended up being this sort of negative number, and so we would end up going, oh yeah, it's coming inwards. Okay, remember negative for electric fields, if you're using signs, we'll give you an inwards thing. Okay, now questions 12, 13 onwards is talking about potential. We're not onto that yet, so we will finish the video there, and we will do more on this later after we cover the next section. Thanks guys, study hard, remember, ask questions, try the tech questions as hard as you can, and don't forget your homework. Thanks, bye.